Swayam Prabha. Digital India. Educated India.
So in the last lecture, I was talking about random variables and some examples of random variables. We'll continue from there, and then we'll talk about stochastic process, definition of stochastic process. So let x to be a random variable. Okay, so I call this x is a random variable. Then a mathematical mapping of y defined as this. For a random variable x, a mathematical mapping of this expression defines a stochastic process. Okay, so you can see there is a function f which involves both this random variable x, also time. Okay, and that mapping we call it as y x of t. This x accounts for the random variable, t is for time. Okay, so the only difference here we are seeing is the time also becomes one of the variables in the process. Okay, so that's when we say this is a stochastic process. Then y x of t is a random function or a stochastic process. So without this x, it would be a regular mathematical function. Okay, now having this x as a argument in this function makes it a stochastic process. Okay, now if I substitute for x some value small x, then I get one realization of this function. Okay, so this is a definition of a stochastic process. Now x can assume any value as per its definition. This x can be a normal random variate, or it can be an exponential random variate, or it can be a uniformly distributed random variate. And if I assign any particular numerical value, then this function gives me a numerical expression, and that is one realization, one sample of the stochastic process. Okay, so we call this as a realization or sample function. Note that time here is a natural variable. Just like how we manage time in differential equations, the same way we manage time here, okay, as a natural variable. Now, having defined a stochastic process as this, now we can ask what is the mean, what is the variance, and what are the correlation functions for this stochastic variable. So we define average as the following. So for a stochastic process defined here, the mean value, okay, is defined for each time. At any given time, if you want to find the mean value of that, what you do is you basically integrate this sample function weighted by the probability density function for x. Okay, this one is a probability density function for the random variable x. Okay, and then it is integrated over all possible values of x, and you can replace this y x of t as the mapping function f of x of t like this. Okay, so that's how you get the mean value of a stochastic process. Sometimes we are also interested in autocorrelation functions. This autocorrelation function tells us the behavior or the response at two time interval, at two time points t1 and t2. Okay, you're looking at the response at one time and another time, and what are the correlation between these two time points. And this is defined as so the autocorrelation function is defined as the mean of the product of the functions at t1 and t2 minus the product of the mean itself at those times t1 and t2. Okay, so this is the definition of autocorrelation function. Suppose if I make t1 is equal to t2, what happens? What can you say about this autocorrelation function? What is this? This is variance, right? So you can see variance becomes a limiting property of an autocorrelation function. Okay, so variance is correlating the variable with itself at the same time, whereas autocorrelation function correlates a function separated by two time intervals. Now I'll give some examples for this function, and then we will do some exercise of how to calculate mean and autocorrelation function and variance. So this is the most simplest possible way is to write something like this. A stochastic process written as some time function times multiplied by a random variable. So x will have to be now qualified. What is this x? Is it a uniform random variate or exponential, or very many kinds are possible. So let us not specify this right now. We'll apply this formula for mean and correlation for this function and obtain it, and then we'll see how this operation is to be done. So now let's say that I want to calculate the mean or average. So that is y of t, and I am going to use this formula here. So in this case, f of x is nothing but phi of t times x so this t can be taken out. Okay, this is a time dependent function, it doesn't depend on the random variable, so this can be taken out. So we see phi of t and what is this? This is simply a mean of x. So the mean of the random function is nothing but the mean of the random variable multiplied by the time function. Okay, remember this is a function of time t for this particular example. This is the variance. Now we can obtain this mean square, and the mean already we know, and then we can substitute and get what is the variance. So the mean square in y is nothing but phi square t times the mean square in x. So we can now substitute it in here. So the variance in y, the stochastic variance in y is nothing but the variance in x multiplied by the phi square t. Okay, so this function is we have not defined, but it will be some function of t. For the autocorrelation function, we will first get this one. So in this expression, I have obtained this mean of the product y of t1 and y of t2, and it basically splits into y of t1 times y of t2, sorry, psi of t1 times psi of t2, mean square x, and we substitute this in the definition, and you will see that the autocorrelation function is nothing but phi of t1 times phi of t2 into sigma square. So now if I substitute t1 equal to t2, then you would recover this function. Okay. So this is an example for a given random process. You should be able to get all the properties you want: mean, variance, autocorrelation function, higher order moments, all that you can apply through this kind of mathematical procedure. So here is another example of a stochastic process, and it is defined with two random variable x1 plus x2 times t. Okay, and we also specify what is x1 and x2. x1 and x2 are random variable which are normally distributed, and they are independent, and both have the mean and variance of 1. Okay, so we are fully specifying the stochastic process. In the previous case, I did not say what the time function was, I did not say what the random variable properties were, but here we are specifying a little bit more. Okay, we are saying what the mathematical function is, it's just linear in t, and we also say what are the random variables are and what are the properties are. So it's a fully specified problem, right? So suppose if x1 and x2, if they were to be constants, okay, and a function like this, if I were to plot y versus time, right, so it will be like a straight line, deterministic. Okay, no uncertainty about it. Tell me a time, I will tell you what the value of y is. Okay, but now when x1 and x2 are random variate like this, and you will see that the slope will be on an average 1, because the mean of x2 is also 1, but then the response you will see quite irregularly, okay, in one realization. If you make another realization, if you do another experiment and create this path, it would be something different. And this is what I meant by uncertainty and irregularity in the dynamics. Okay, and an average mean value you will find will be just 1 plus t. Okay, because mean of this is 1 and mean of this also 1, so the average behavior will be 1 plus t. That's what this line is. But then if you look at the instantaneous realization, it's going to be like this. Okay, now you can write any other function of your interest depending upon what physical model you want to predict, what biological model you want to write, what chemical model you want to write. Okay, so now we will take this definition and we will apply the same thing and obtain what is the mean characteristics, what is the variance here, and what is the autocorrelation function, and so on. You can try to do this by yourself and then you can check for your answer here. The independent characteristics is very important, because I don't have to write a joint distribution. I can write the joint distribution as a product of the two distributions. Actually, in one of the previous classes I mentioned some of the properties of independent distribution is that you can write the joint distribution as product of individual distributions, and that's what I'm using here. So that's why this independence is important. Suppose if we didn't mention this, then we have not fully described the problem, because then I have not mentioned anything about the joint distribution function. Okay, but now this independence gives me, the independent nature of the distribution gives me that I can write x1 and x2 distribution as a separate distribution, and this is a normal function, normal distributed random variable. you have to note that when we write this expression, there are two variables we have to integrate over, dx1 and dx2. So this is actually double integral. So what I have done here is I have opened this up. I am first writing this x1 term. So x1 times px1 px2 dx1 dx2 plus the second term, which is x2t multiplied by px1 px2 and dx1 dx2. So if you look at this, now you can separate the integral. You can separate the x1 term separately and x2 term separately. So you see that the first integral contains only x1 and the second one contains only x2, okay, because there is no interdependence here. I can separate this function. And what is this? The integral of px2 dx2 is 1, okay, because the integral of the distribution function should give me 1 unity. And similarly in the second case, I am separating the x2 term and x1 term, and here this is going to give me 1 unity. That is a property of the probability density function here. So what is remaining here is, and also I have taken the t outside because t does not depend on x1 and x2. So what I have is, what is this one? This is a mean in x1, and I already mentioned mean is 1. So this term is going to be just simply 1. Here I have t. This term already I said is 1, and this is mean of x2, which is also 1. So I am getting basically the mean of y is simply 1 plus t, what I have drawn in the function before, okay. It is basically linear in time t. This is the mean behavior of y. We will carry out the same procedure for the variance and autocorrelation function. For the variance, I need mean square. We will open this up. Since in the previous case I explained how to open this up and separate the variables, we can directly write what is going to be the surviving terms, okay. So this one will simply become mean square in x1, okay, because when you integrate over x2, it would become 1. So this is the only remaining term. In this case, you will have t square and then you will have x2 square. Here we will have 2t, and then you have a mixed term x1 and x2. So you would have separated x1 p1 and then x2 p2. You would have product of the two means x1 and x2, okay. So now we can substitute the values, t plus 1 whole square. No, it is just a statistical property of x1, it does not depend on the time. You have to just tell this from this information. Mu is 1, sigma square is 1, so mean square will be 2, right. So this is 2, this is also 2, these are 1 each. So you have 2t, okay. So essentially 2 times 1 plus t square, okay. So that is your y square. So variance is nothing but mean square minus square of the mean. The mean is 1 plus t, the square of it is 1 plus t square. So in this case, we write the expression for the autocorrelation function. From here, we don't have to again go through this integral formula, all that. We can simply try to, based on the properties of the random variable, we can directly multiply here and apply the mean operation. And for example, in this case, what will happen is, so you would multiply x1 in x1 squared, and that would be mean of that. So that is the first term. Okay. Then you multiply this and t1. So you multiply this and this, you will get t1 and x1, x2, the mean of that. Okay. So that's what this is. And similarly, you can continue this operation, and you will get here. From here to here, all I have done is I have substituted the numerical value. Mean square in x1 is 2. t1 remains as such, but this can be written into mean of x1 times mean of x2 because they are independent variables. Okay, it's 1 times 1 is 1, so you have only t1. Similarly, here you have only t2. So here we have mean square in 2, which is this is numerically 2, so it will be 2 times t1 t2, and then same for this. And then when you simplify this, you will get 1 plus t1 plus t2, and if you substitute t1 and t2 equal to t, you will get 1 plus t square. That should be same as the variance. Okay. So the third example is a sinusoidal function. So sin omega t, it's a signal with a noise. Okay, y of t equal to sin omega t would be a sine wave, but here I am adding a random variable here. This random variable is a uniformly distributed random variable over a range of 0 to 2 pi. Okay, so if you plot this, you will see an average a sinusoidal wave, but then there will be fluctuation around it. There will be irregularities around this. Okay, so this is for you to do exercise. You find the mean, variance, autocorrelation function, show the results, then you can leave. Okay.